In this module, we will talk about molar heat capacities of solids, and also later on we will talk about electronic partition function. If you recall, in the earlier module, we talked about vibrational partition function and the molar heat capacities of gases. Why we are talking about molar heat capacities? There is a reason. The reason is that molar heat capacities can be experimentally determined. And since they can be experimentally determined, they are going to provide a testing grounds for verifying the theoretical statistical mechanics results. So to what extent statistical mechanics results are correct or not, it can be known through experimental determination of the molar heat capacities. After having discussed the molar heat capacities of gases, let's start with the molar heat capacities of solids. But before we do that, let's recapitulate some of the definitions which we talked about in the last module. You already know that heat capacity of any substance is the heat required to raise its temperature by 1 degree centigrade. This is a very general term. Specific heat capacity of a substance is the heat required to raise the temperature of 1 gram of a substance through 1 degree centigrade. And the molar heat capacity is the heat required to raise the temperature of 1 mole of the substance through 1 degree centigrade. So these are some of the fundamental definitions which we have already talked about. Now let's proceed to the molar heat capacities of solids. In the case of solids, there is a very well known famous Dulong and Petit's law. According to this law, which was proposed in 1819, specific heat capacity of a solid element is always equal to 3R by M, where R is the gas constant and M is the molar mass. So this was Dulong and Petit's law. So as you can see here in equation 1, Cs, that is the specific heat capacity of a solid, is equal to 3R by M. Or if we take M to the left hand side, we get equation 2, which is Cs multiplied by M gives us 3R. That is, if we substitute the value of R, which is the universal gas constant, it becomes 6 calories per Kelvin, or in terms of joules, it becomes 25 joules per K. So left hand side Cs multiplied by M is the molar heat capacity of a solid. Now you notice here that according to the Dulong and Petit's law, molar heat capacity of any solid element you may take will always be constant and will be equal to 3R. Here one can notice that one can find that molar heat capacity according to this law should be independent of temperature. But is this true? Experimental determination has shown that molar heat capacity of a solid does change with temperature. As you can see here in these plots, here in these plots, as you can see, we are plotting molar heat capacity versus temperature, and these plots are for different elements. You can see diamond is there, silicon is there. All these elements show the variation of the molar heat capacity with temperature. So one thing is clear, that molar heat capacity is not independent of temperature. It does depend upon temperature. So why it happens so? That is something which we would like to know. According to Dulong and Petit's law, it should be constant. If you go into the explanation of Dulong and Petit's law, it is based on, classical theories according to which every atom of the solid can be treated as a linear harmonic oscillator with 6 degrees of freedom, and each degree of freedom according to the equipartition principle will contribute half kBt, where kB is the Boltzmann constant. Therefore, molar heat capacity Cv we are writing, that is at constant volume, that becomes, as you can see here in equation 3, Cvm, there is a contribution from translational degrees of freedom, then the contribution from rotational, and then from the vibrational. And since there are 6 per atom, and for 1 mole it will become 6 into, you can see, ultimately by half by r, though it becomes 3r. That is basically what Dulong and Petit's law states. But as we showed you from the plots, this should not be constant. So how do we explain the variation of the molar heat capacity of a solid element with temperature? That's the next question. To explain this, Einstein proposed a theory which is known by the name Einstein theory of heat capacity of solids. What he assumed was that a solid element, if you take 1 mole of the solid element, that can be taken to be a non-linear solid. And suppose it contains Na atoms. Let's talk in general. Suppose that non-linear solid contains Na atoms. Then, as you can see here, for a non-linear solid, there will be 3 translational degrees of freedom, there will be 3 rotational degrees of freedom. Had it been linear, it would have been 2 rotational degrees of freedom, and the remaining 3 Na minus 6 will be vibrational degrees of freedom. For a linear solid, it would have been 3 Na minus 5. So that is how Einstein started his theory. So once we know the degrees of freedom in an Einstein solid, then the total contribution to the heat capacity will be from these degrees of freedom, and that means Cvm, that is the total molar heat capacity at constant volume, will have Ct, that is the translational contribution, plus Cr, which is the rotational contribution, and Cv, which is the vibrational contribution, as you can see in this equation. Now, if we take half kb to be the contribution for each degree of freedom, for translational as well as for rotational, then for this nonlinear solid, Cvm becomes 3 by 2 kb plus 3 by 2 kb. These two terms are contributions from translational and rotational, and the remaining vibrational degrees of freedom will contribute. If you are able to recall what we have learned in the last module, the contributions will be kbf. So for 3 Na minus 6 vibrational degrees of freedom, the contribution will become 3 Na minus 6 kbf, where f is the Einstein function and its expression is shown, as you have already learned in the last module. In this equation, if you see, where we are giving the expression for Einstein function, theta v is the vibrational temperature, which is HVB upon K, and rest of the terms we already know what they mean. And if you are able to recall, in the last module we also noted that this Einstein function has a value which ranges from 0 to 1, and this changes because of the change in temperature. Now we can further look into this equation and notice the following. As you see here in equation 7, Cvm, that means the molar heat capacity, now becomes 3 kb plus 3 Na kbf minus 6 kbf. we have opened the brackets and this is what we get. And this further simplifies to give you 3 NaKbF plus 3 minus 6 FKb. This is how the simplified form looks. Now, since Na is very large, number of atoms in 1 mole will be Avogadro's number. Therefore, if you look at equation 8, you can very well appreciate that the second term, that is 3 minus 6 FKb, that is negligible as compared to the first term, and therefore the expression for the molar heat capacity at constant volume for an Einstein solid reduces to, as you can see here, CVM is 3 NaKbF as shown in equation 9. And since for 1 mole Na is Avogadro's number, therefore NaKb will be equal to universal gas constant, and therefore CVM becomes approximately equal to 3RF, where F is the Einstein function, R is the gas constant, and this is shown in equation 10. So now, since we know that F, that is the Einstein function, varies between 0 to 1 depending upon the temperature as shown in this figure. Therefore, you can very well imagine from this equation that molar heat capacity at constant volume will be varying between 0 to 3R. As you can see here, when F is 1, the molar heat capacity will become 3R, and when F is 0, molar heat capacity will become 0. Therefore, Einstein was able to explain the variation of the molar heat capacity of solids with temperature on the basis of his theory. And please remember, this could not be explained by Dulong and Petit's law. If we want to go into the details of the change in the molar heat capacity with temperature, we can consider two cases. First case is, as you can see here, when the temperature is very high. When the temperature is very high, theta v by T in the Einstein function will become very small. And therefore, as you can see in equation 11 and equation 12, Einstein function reduces to e to the power theta v by T. And since temperature is very high, therefore e to the power theta v by T ultimately tends to approach e to the power 0, because T is very high and that becomes 1, and that is F tends to approach 1. That means at high temperature, as you can see here, molar heat capacity tends to approach 3R because F approaches 1. And now let us consider case second. That is the case when the temperature is very low. And if temperature is very low, you can see theta v by T will become very large. And once theta v by T becomes very large, e to the power theta v by T will become again very large, because this is the term which appears in the Einstein function. Now, if we look at the expression for the Einstein function, you can see in equation 16 that this equation gets modified and we have F is equal to theta v by T whole square into 1 upon e to the power theta v by T. That is what the equation 16 is. If we expand the denominator in this equation, as we are doing it in equation 17, F becomes equal to theta v by T whole square into 1 upon e to the power theta v by T, which ultimately becomes equal to theta v by T whole square into 1 upon 1 plus theta v by T plus theta v by T whole square into 1 upon 2 factorial plus so on. So that is how the expansion will look like. And if it is rearranged As you can see, we have done it in equation 18. This equation gets further modified, and since T by theta V is very small, because we are considering a case of very low temperature, therefore F will tend to approach 0. So this is a very important point, that when temperature is very low, Einstein function tends to approach 0. Whereas when temperature was very high, Einstein function approached 1. And now in this case, once F approaches 0, then the molar heat capacity CVM will ultimately approach 0. Therefore, one notices that Einstein theory of heat capacities of solids explains the variation of molar heat capacity with temperature. And one must also notice that this variation arises primarily because of the vibrational degrees of freedom. It's basically the vibrational contribution which accounts for temperature dependence of the molar heat capacity. However, you must notice that Einstein theory also had certain drawbacks. What are those drawbacks? Number one, the drawback is that Einstein considered vibrational degree of freedom of one particle only and then extended it to the remaining 3Na-6 degrees of freedom. So it was just extension. That is one drawback. Second drawback is that all the 3Na-6 vibrations were assumed to be having the same frequency. Because if you remember, vibrational temperature theta V was always taken to be the same for all vibrational degrees of freedom. This, you will agree, may not be true. Even for a simple molecule like carbon dioxide, we have symmetric vibrations, we have anti-symmetric vibrations, we have bending vibrations, so they are with different frequencies. But here Einstein assumed all vibrations of equal frequency, so that is another generalization and a drawback. And the third serious drawback was that the vibrations were assumed to be simple harmonic, which may not be true, because simple harmonicity is something very ideal. So this was another drawback of Einstein theory. All these drawbacks were later on taken care by Debye in his model. However, this Debye model we are not going to discuss here, and you will study it later on. Therefore, to sum up, one can say that in the Einstein theory of heat capacity of the solids, we are able to find out the range of the molar heat capacity values, and we notice that the molar heat capacity varies between 0 to 3R. 0 is the case when the temperature is very low, and 3R is the case when the temperature is very high. Having studied molar heat capacity of the solids, now we move to the next topic, and that is the partition function. And here we will talk about electronic partition functions of the particles. If you recall, in our earlier modules, we have always studied that if a bulk system is taken, and bulk system contains either monoatomic particles or polyatomic particles, in the case of monoatomic particles, the only partition function which we considered was translational partition function, because a single particle can have only translational motion. So Q was equal to Qt. And in the case of polyatomic particles, we took, besides translational, rotational and vibrational degrees of freedom. That means the partition function was Q is equal to Qt, which is the translational, then QR and QV, rotational and vibrational contributions. In all these partition functions calculations, we never considered the internal structure of the particle. That was never taken into account. Every particle, you know, has electrons, it has nucleus. Therefore, these internal structure were ignored in all these partition functions. But then one can always ask whether these internal structure, our electronic and nuclear motions will also contribute. That is what we are now going to study. And if these are taken into account, the expression for the partition function gets modified, as you can see here in this figure. Here you can see that last two terms come in the monoatomic particles, that is Q is equal to Qt, which is what we were already considering. Then it comes QE and Qn, electronic and nuclear partition function. The same thing comes for polyatomic also. Q is equal to now Qt, QR, QV, and then Q electronic and Q nuclear. So now the question comes, what is electronic partition function? How can we calculate it? And similarly, what is nuclear partition function and how to calculate it? Now we will discuss about this. If you look at the electronic partition function, you can know, as we have done in our earlier studies, the general expression for the electronic partition function is as shown in expression 21. QE is equal to summation I GE e to the power minus epsilon E upon KB by T I. Here I are the various electronic states, and so summation is taken over all electronic states. If we expand this equation, this becomes, as you can see in equation 22, QE is equal to G0. G0 is the ground state degeneracy of the electronic state. Then e to the power minus epsilon 0 upon kBt plus G1. G1 is the electronic degeneracy of the first electronic state, then its energy epsilon 0 1 and like so on. So that is the expanded form, and the summation will be over all electronic states. In the case of translational, rotational and vibrational motions, if you recall, there were certain expressions which we use, general expressions. For a particle in a box was used, for translational, then for rotational also something was used, and for vibrational also. But a general expression cannot be used here, because there is no general expression for electronic energy. Electronic energy, as you know, is calculated by the solution of the electronic Schrodinger equation. And electronic Schrodinger equation cannot be solved for any system containing more than one electron. Therefore, only approximate methods are used. But one thing which one needs to remember is that electronic states are very widely spaced. They are much higher in energy, because going from ground electronic state to the first excited state means changing the electronic configuration itself, and that will require a lot of energy. Therefore, one can say that electronic states are widely spaced apart. The energy difference between the successive energy states which are electronic in nature is very, very large. This is something which one must keep it in mind. Now, if we do that and bring all energies to the same zero, because translational, rotational and vibrational, they were measured at some 0th of the scale. If electronic energy is also brought to that, so that the ground electronic state becomes 0, then the rest of the energies will be the energy differences, and the expression will look as you can see here. This is how the expression would look. But since energy spacing is very, very large, therefore except the first term, all higher terms will become almost negligible, because they all have exponential with a negative sign, so the contribution becomes very, very small. So neglecting them, ultimately the expression for the electronic partition function becomes Q is equal to G0 into e to the power minus epsilon 0 upon kBt. That is equation 23. Here epsilon 0 is the ground state electronic energy. But if the ground state electronic energy is brought to the level of the 0th of the scale, then this will also become 0. So all will be measured relative to the same scale, and therefore once this becomes 0, electronic partition function will become, as you can see here, QE will become equal to G0 e to the power minus 0 upon KB by T, that is G0. That means electronic partition function is equal to degeneracy of the ground electronic state. That is what we ultimately conclude. And this is a very, very important result which one must remember. And please remember, degeneracy is only a number. So this will be just a number which one needs to calculate. Now the question comes, how to know the degeneracy of the ground state? There are various methods which you have already studied, as you have done. If you do the Russell-Saunders coupling, there you can find out the degeneracy of the ground electronic state. There are well-known expressions. Generally, the states are doublet, as you can see here in the case of hydrogen atom. The degeneracy is given by 2J plus 1, and J here comes out to be half, and therefore degeneracy comes out to be 2. Similarly, for most of the molecules and stable ions, ground state degeneracy is 1 because they are non-degenerate states. So these are well known, and therefore the corresponding degeneracy of the ground electronic state can always be known very easily. Now you will agree that once we know the electronic partition function, can we calculate the bulk thermodynamic properties arising because of this? That's the next question. Yes, one can do, and the expressions we have already used many times in our earlier modules, and let's try to calculate each of the bulk properties one by one. Energy, if you see, as it is shown in equation 25, this is the expression which we have been using always. In this expression, if we now substitute electronic partition function, which is now equal to the degeneracy of the ground electronic state, and let's see what happens. So this is the expression for the energy, and that comes out to be ultimately, on simplification, E is equal to NKB T square delta ln G0 by delta T at constant volume. Why this is coming out 0? Because you are taking differential of a number. Degeneracy is just a number, therefore it makes 0. Therefore there is no contribution to the electronic energy coming from the electronic partition function. This is a very important result. Similarly, one can calculate another bulk property, that is the entropy. As you can see here, we know the expression for entropy given in equation 28, and if we substitute the values of the electronic energy and the corresponding electronic partition function, we get expression which is given in equation 29, which is NKB ln QE, that is basically the contribution to entropy. Heat capacity, can you guess, will there be any contribution? No, because heat capacity involves differential with respect to temperature, and differential of any number with respect to temperature will be 0. Therefore, as you can see here in equation 30th, molar heat capacity contribution because of electronic partition function will ultimately be 0. Similarly, there are other thermodynamic properties which we have talked about. You can calculate all of them using the same principles. So in this module, we have discussed today the molar heat capacities of the solids. Why we are laying so much emphasis on the molar heat capacities? Because these are experimentally determinable quantities, and they provide the testing grounds for verification of the statistical mechanics results, which are theoretical. That is why we are learning all that. We talked about Dulong and Petit's law, which states that the molar heat capacity of any solid should ultimately be equal to 3R. But it could never account for the temperature dependence. Then we talked about the Einstein theory of heat capacities of the solids, and we showed how Einstein theory explains the variation of the molar heat capacities of the solids with temperature. And the term which was responsible for this variation was the Einstein function, which comes from the vibrational contribution. And we noticed that the Einstein function varies between 0 to 1. 0 at very, very low temperatures, and 1 at very high temperatures. But at the same time, we also noticed that Einstein theory had certain drawbacks. We highlighted them, and then these were ultimately modified. Lastly, we talked about the partition function, the electronic partition function, because for the first time we took into account the internal structure. And we showed that the electronic partition function for any atom or any chemical species ultimately is equal to the degeneracy of the ground electronic state. Using this partition function, we calculated the various bulk properties and their contribution. So that is all what we have discussed in this module. In the next module, we will talk about the nuclear partition function and some other terms.